This is Physics 2212, Lab 2. The purpose. So the purpose of this lab is to see how the magnetic field of a bar magnet changes with distance from the observation location. We're going to use a magnetometer app on our phone to collect data. Then we're going to apply the Bois-Savart law to calculate the magnetic field, and finally compare these results with the results of a computational model. All right, so key concept. Well, first of all, the most important one is Bois-Savart's law, seen here. And second of all, we need also the formulas for the magnetic field of magnetic dipoles, which is what a bar magnet is. Here is our on-axis one and our perpendicular axis. We're going to be using the on-axis one. All right, so preview plus assumptions. Our preview showed that as the magnetometer moved closer to the magnet, the measured magnetic field increased. When the magnetometer is infinitely far away, the magnetic field is going to be zero. So basically, it's just going to decrease as it moves further away. And here are results at the end, the graph, but assumptions. First of all, the bar magnet can be treated as a perfect magnetic dipole. And two, there are no external forces except the magnetic force from the bar magnet. So we're going to say that there's no other magnetic fields acting at all in the room. So with our experiment, the system is the magnetometer. I think I misspelled it. Anyway, the surroundings is the bar magnet plus everything else. And initial conditions, our phone is going to be placed on the ground on the east-west axis. So the procedure, firstly, we're going to use the that's how you spell it, magnetometer app on a device and measure magnetic field at the location. Two, we're going to measure the distance between the device and bar magnet. And three, we're going to measure the y component of Earth's magnetic field and move the magnetometer there. So here's our data. You can see the graph and the data here. Yeah, I cut it off by accident. But... All right, so here's the computational model. Where we're basically going to make arrows for every one of every kind of direction we need to know, where the on-axis is, where the dipole is going to be, all that kind of stuff. Cool. And here's the result. So talking about the results, we found that the x component of the magnetic field decreases as distance between the magnet and the device increase. I found that the value of n is roughly minus 2.95. The magnetic moment of the magnet, which is denoted by symbol mu, is around 1.79 amperes meters squared. And the measured off-axis magnetic field is 6.69 times 10 to the minus 5 Teslas, and the simulated magnetic field is 2.63 times 10 to the minus 5 Teslas. And these are going to be very small amounts because Tesla is a very, very large unit. So this was about expected. I mean, it's pretty close. But it's not the same. So there must be some sources of errors. And I think one, and the most likely one, is human error in the sense that the phone was rotated slightly. I don't know, or rotated, tilted. That's what it meant to say. Or rotated slightly, which can change the reading. Um, where the sensor is, might have been also placed wrongly. That kind of other human errors. Calculation error is also possible. That's all part of human error. But also most likely there are other magnetic fields present from nearby objects in the room. So, I mean, this could be like any usually metallic or conductive object, right? So let's talk about our what ifs. Firstly, in the experiment, you oriented your setup as to compensate for magnetic north. What if you hadn't done that and had instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? How the results have changed? Well, the x and y components of the field would be different because they're in different directions. But the z component would have remained the same as long as it's still conducted on a flat surface because it's going to be the same. Okay, and then what if, imagine you had two identical magnets. What if you redid the experiment, but instead of using a single magnet, you used two identical magnets stuck together end to end? How do you expect your measurements to differ? Well, essentially, if you use two identical magnets stuck together, they become one big magnet, right? So the magnitude of the magnetic field would increase due to an increase in the magnetic dipole moment, but the direction would remain the same.